Hi, I am Meghana Shadakshaya from Friedrich Alexander University, Erlangen. I'll be talking about neural radiance fields, a new scene representation for view synthesis. In this talk, we are going to focus on the problem of view synthesis and how to find the related dataset for future relevant studies. All the information discussed here is the work done by a group of researchers from University of California, Berkeley and Google Research. Neural radiance fields are abbreviated as NeRF. NeRF represents a scene as a continuous volume of particles that emit light. Rendering a ray that passes through a NeRF is simple. You just sample points along the ray, and the final color is the sum of the light emitted by particles at each point, multiplied by how much that point is blocked by closer samples. NeRF works well for rendering the same scene from novel viewpoints, but does not give us a way to simulate how any point's appearance changes with new lighting conditions to enable relighting. So let us look at the key points that are discussed in this talk. Those are introduction about the topic, the related work, discussion on results, about datasets, and conclusion. First, let's look at our continuous volumetric scene representation. We represent any arbitrary scene as a simple, fully connected network. Just a layers of 256 channels each. This network takes in a continuous 5B coordinate that consists of a 3D location XYZ and a 2D viewing direction theta and phi. The network outputs the volume density sigma of particles at that location as well as an RGB color that represents the radiance emitted by a particle at that input location and along that input direction. Coming to the second image in the slide, here we synthesize views by querying 5D coordinates along camera rays and use classic volume rendering techniques to project the output colors and densities into an image. Because volume rendering is naturally differentiable, the only input required to optimize our representation is a set of images with known camera poses. Also, we describe how to effectively optimize neural radiance fields to render photorealistic novel views of scenes with complicated geometry and appearance and demonstrate results that outperform prior work on neural rendering and view synthesis. A promising related work in the domain of computer vision is encoding objects and scenes in the weights of an MLP that directly maps from a 3D spatial location to an implicit representation of the shape, such as the sign distance at that location. However, these methods have so far been unable to reproduce realistic scenes with complex geometry with the same fidelity as techniques that represent scenes using discrete representations such as triangle meshes or voxel grids. A similar approach of using MLPs to map from low dimensional coordinates to colors has also been used for representing other graphics functions such as images, textured materials, and indirect illumination values. Neural 3D shape representations has investigated the implicit representation of continuous 3D shapes as level sets by optimizing deep networks that map XYZ coordinates to signed distance functions or occupancy fields. These models are limited by their requirement of access to ground truth 3D geometry, typically obtained from synthetic 3D shape datasets such as ShapeNet. In view synthesis and image based rendering, given a dense sampling of views, photorealistic novel views can be reconstructed by simple light field sample interpolation techniques. For novel view synthesis with sparser view sampling, the computer vision and graphics communities have made significant progress by predicting traditional geometry and appearance representations from observed images. Coming to the results section, here are results on synthetic dataset of path traced objects with realistic non-Lamboschian materials. The next is view dependent appearance. Here we can visualize the view dependent appearance encoded in our nerve representation by fixing the camera viewpoint but changing the queried viewing direction. This is geometry visualization. Nerves are able to represent detailed scene geometry with complex occlusions. Here we can visualize depth maps for rendered novel views computed as the expected termination of each camera ray in the encoded volume. Here we can see the estimated scene geometry is detailed enough to support mixed reality applications such as inserting virtual objects into real world scenes with compelling occlusion effects. This shows 360-degree scene capture with real data. Nerves can even represent real objects captured by a set of inward facing views without any background isolation or masking. Authors of this work have given access to a fantastic nerve dataset, which are further classified into synthetic renderings of objects and real images of complex scenes. Under synthetic renderings of objects, you can find two different categories, that is synthetic and real 360 dataset. Synthetic dataset has images of chair, drums, ficus, hot dog, Lego, materials, mic, and ship. And coming to the stats of this dataset, it has 8 scenes, 100 training images, 100 validation images, 200 test images, and each image is of 800 cross 800 pixels. The dataset real images of complex scenes has results on complex real world scenes captured with roughly forward facing images. This dataset consists of 8 scenes captured with a handheld cell phone, 5 taken from local light field fusion, and 3 that they have captured with 20 to 62 images, and hold out 1 by 8 of these for the test set. And all the images are 1008 cross 756 pixels. And this LLFF dataset, that is local light field fusion, has images of fern, flower, fortress, horns, leaves, orchids, room, and treks. So, this is the brief description about the dataset which can be utilized for further studies. To conclude, representing scenes as 5D neural radiance fields produces better renderings than the previously dominant approach of training deep convolutional networks to output discretized voxel representations. Sample representations such as voxel grids and meshes admit reasoning about the expected quality of rendered views and failure modes. This work progresses towards a graphic pipeline based on real world imagery, where complex scenes could be composed of neural radiance fields optimized from images of actual objects and scenes. All the content of this work has been taken up from the GitHub page mentioned here in the slide. I sincerely thank authors of this work for publishing, and thank you so much for your attention.